Welcome to Ansys tutorials by Civil Thinking, and this is our second class on Ansys tutorials. Now before I move on, I suggest to you to please watch the video lectures on Ansys tutorials one by one in sequence as in the playlist so that you understand better. The playlist link is in the description, or also you can click on the pop-up on your screen. Now in the previous class we have talked about engineering product, why it is better to design and test an engineering product in the Ansys program. And now in this class we will see how does Ansys work. Okay, now Ansys basically work on something we call it as finite element method or analysis. Okay, FEM or FEA. Okay, finite element method or finite element analysis. Okay, now Ansys work on based on this principle. Okay, and it is a numerical method. Okay, numerical method. Now before we go deep into this, let us explain this. An engineering product is made to fulfill the purpose of its manufacture without failure so that our problem is solved. Now in previous class we talked about engineering product, right? Engineering product, or I will write it as EP. Okay, now we have this engineering product. Now the question is, why do we build it? Okay, why do we build or construct it? Okay, now this is the question. Now we know any engineering product, why do we construct it? Right, now we know necessity is the mother of invention. Okay, because we have some problems and we want to solve this problem. So how do we solve this problem? We manufacture. Okay, we invent an engineering product, right, so that our problem is solved. For example, let us talk about a beam. Now what is beam? It is an engineering product, right? EP, right? It is also an engineering product. Now why do we build it? Because we need a beam, okay, to support some loads, right? Let us say this is a load. Okay, now consider this as a shelf. For example, a shelf. Now we build this so that we put some things on it so that it can safely carry these items, right? That's why we invent this beam, right? Now we know, because when the load is applied, this load will try to deflect, right? It will try to deflect this beam like this, right? And if the deflection is more, it will try to deflect it like this. Okay, let us say the deflection is y. Now if y is more, okay, the beam may fail, right? Beam may fail. And when the beam fails, what happens? It did not serve our purpose. Okay, it failed to serve the purpose, right? Serve the purpose, right? Now maybe we bought this beam. Okay, we got, you know we told the construction company to build something beam in our home or in our office or wherever, because we needed these items, we needed this beam to carry the load of these items. Okay, for example, a bridge. Why do we build a bridge? So that it can easily let the traffic on it, so that it can let the traffic to go from this point to this point, right? Now what happens if this engineering product fails? It means it has failed to serve the purpose, right? So our money is wasted, right? So before constructing an engineering product, okay, before before it is manufactured, okay, before it is manufactured, we have to test, we have to test if it it is strong enough to fulfill its purpose, right? We need to know if this engineering product is okay to fulfill our purpose or not, okay. Based on our requirements we will design it, okay. So first of all we have to test it, right? We have to test it virtually and see if it fulfills the purpose, if it does not fail, okay. So for example in this beam, if this y is in permissible limits, okay, permissible limits, what does that mean? It means this product is okay, right? So we have to check, we have to analyze this beam for what? For its strength, right? Now let us talk about this beam. For example, now let me draw it as a line, okay. Now when you apply the load on it, for example you apply a UDL on it, okay. Now let me tell you, I am explaining, okay, you know, in very basic level so that you understand the basics of the analysis, okay, basics of the Ansys program, okay. Because you know, let me tell you, you don't have to worry much about all these details in the Ansys program actually, but right now we are laying the foundation of the Ansys program. Why on the first hand do we use it, okay? How does it work? Because if we don't know how does it work, we will never be perfect in it, okay. So this lecture is very important if you want to, you know, learn the background behind the Ansys, okay, how does it work. Then you will solve any problem because you know how it works, okay. Now coming to this, now let us say we have this beam and we apply load, okay. Now of course it will deflect, right? It will deflect, okay. Now we have to see if this deflection is in permissible limits, right? Let us say this is y, it is the maximum deflection. We have to check it if it is in permissible limits, okay. Let us call this as y max, okay, because deflection will be maximum at this point. Now let us say at any point x the deflection is y, okay. What does it mean? At a distance of x from this left support, this point on the beam, let us say this is point 1, it has deflected to 1 dash, okay. Let us say this point is 2 and it has deflected to 2 dash, okay. So what we need now, we have to check if it is in permissible limits, right? So we now have two methods here, okay. One is analytical method and another is numerical method, okay. Numerical method. Now what is analytical method? Analytical method, you know, you have studied. Analytical is basically using just, you know, simple formulas, okay. Simple formulas or or differential equations, okay. Differential equations, okay. Now let us talk about this. Now you know, if you want to find the deflection of a point in a beam at a distance x from the support, then we know according to, for example, Macaulay's method. Macaulay's method, for example, we know m is equal ei d square y divided by dx square, okay. Now this is, you might have seen this in, you know, in structural analysis subject. According to the Macaulay's method, moment is equal to EI times d square y divided by dx square. Okay, now we have to find what? We have to find y, right? This y is a function of x, right? And we have to find this, right? Why? Because we have to test if it is in permissible limits or not. Okay, if it is in permissible limits, okay, if this is okay, if y is in permissible limit, implies, what does it mean? Our engineering product is okay, right? Which is engineering product? Here in our case it is beam, right? This beam is okay, right? Now if it is not, if y is not in permissible limit, so will we manufacture this engineering product? No, right? We will not. Why we need it? Okay, because if it has to fail, it will not serve our purpose. Okay, so we have to do the analysis. Okay, so now in analytic method we have this equation. Now here this is the y, we need this y. Okay, now this is d square y divided by dx square. Okay, this is second order differential of y with respect to x. Okay, now what we will do, we will integrate it. Now I'm talking about the analytical method. Now this is how we do integrate, then we will get integration of m is equal to ei times, now integration of d square y divided by dx square is dy divided by dx, right? Now still we didn't get y, right? Because we get now dy by dx, but we need y, right? So what we do, we'll integrate it again, right? So we will here get, it is integral m, so here we will get again another integral, double integral m is equal ei times y, right? Of course there will be some constants of integration. Okay, for example c dash, c double dash, I will not go into these things, this is not important right now. I want to say how we find y using using an analytic method, for example Macaulay's method. Okay, now from here you will get the value of y, right? It will be c double dash plus double integral m divided by ei. Okay, so we get the y. Okay, now this y is exact solution. Okay, this is the exact solution, right? This is our what? This is our differential equation. Okay, differential equation. Okay, so before actually manufacturing an engineering product, we have to solve these differential equations. Okay, because the behavior of these engineering products is determined by these differential equations. Okay, now right here it is simple differential equation. Okay, simple differential equation. Okay, so but it is, we got an exact solution. Okay, this is accurate, y is exactly. Okay, now when I talk about numerical method, I will basically talk about finite element method. Okay, because finite element method is a numerical method and it is used in Ansys program. Okay, now when we talk about Ansys program, or what does it do? If we take the same problem, okay, if we take the same problem here, what does it, we let us see how will FEM solve it. Okay, let me put it here. Now see how it does. Basically when we talk about finite element method, okay, now here is the word finite element. Okay, finite element. Okay, F is finite, E for element. Okay, M is method. Okay, or FEA, finite element analysis. Okay, so what is this finite element? Okay, now let me first tell you like this. Now if we take the same problem, same beam problem, and we want to find y. Okay, now in FEM, what does it do? It will calculate the y. For example, this is 1. Y is the deflection of 1 to 1 dash, right? When 1 moves to 1 dash, we get y deflection. Okay, for example, let's call it this as y1. Okay, now let me call this as y2. Let us say this is 0.3, and it deflects to what? It deflects to 0.3 dash. Okay, now here again the deflection is y3. Okay, so y1 is the deflection when 0.1 moves to 1 dash. Y2 is the deflection from what? When the point 2, okay, point 2 on this beam moves to what? 2 dash, right? Similarly, y3 is what? When point 3 moves to 3 dash, we get y3 deflection. Okay, now in FEM, what does it do? It computes the deflection of each point. Okay, in FEM we call this point as node. Okay, it calculates the deflection of each node. Okay, because we are talking about deflection. Okay, now it could be, for example, if it was not beam, if it was something else, and we needed to find the temperature at different points. Okay, then it would calculate the temperature at different nodes. Okay, now we are talking about the deflection right now, so the Ansys will calculate the deflection of each node. Okay, now this is one node or point, and this is another node. Okay, for example. Okay, now let me erase this. Now this is 1 and this is 2. Okay, now this is node and this is node. Okay, this line connects two nodes. Okay, so this is the finite element. Okay, this is the finite element. Okay, finite element is basically, okay, the line between two nodes, or if it is an area, then this is the area. Okay, then this is the element. Okay, because it connects the nodes. Okay, anyways, this is not important right now. Now what it does, it, instead of this general equation, here we had this general differential equation, right? What it does, it does not use general equation, rather this FEM uses the converted form of this differential equation. Okay, so what it does, so for example, we had differential equation here, then finite element method, what it does, it converts it into uh, linear equations. Okay, set of linear equations. Okay, because linear equations are easy to solve. Okay, easier than differential equation. Okay, now what it does is it calculates the deflection at each point. Okay, using these linear equations. Okay, and then we get these displacements here. Okay, at every point we get displacement, and then we join it, and we get the deflected shape, right? Deflected shape. Okay, so that is the basic difference. What it does here, in analytic method we use differential equations. Okay, but in finite element method it converts the whole product, whole body of the product into finite elements. Okay, this is a finite element, this is also a finite element. Okay, then it calculates the deflection at each point using what? Using linear equations. Okay, basically linear equations in the matrix form. Okay, we will not go into this. Okay, in the matrix form, this is not important. Okay, now so this is the difference. Okay, but this linear equation, then we solve y1, y2, y3. Okay, we get these values. Okay, and here we get the general y, but here we get y1, y2, y3. Okay, now this is what? This is approximate. Okay, this is approximate solution, but in analytic method we get exact solution. Okay, or accurate solution. Accurate solution. This is approximate solution. Okay, why it is approximate? Because we are not basically getting this y1, y2 from the differential equation. Okay, if we got the if we got this y1, y2 from the differential equation, then it would be accurate. Okay, but in the Ansys program or in FEA method, finite element analysis, what we do, we find y1, y2, y3 from these linear equations. Okay, not the differential form. So this is an approximate solution with small, variation, a little bit. The solution here is a little bit different, from exact. Okay, so we have a small error. Okay, now when we talk about this error, when we have very little error. Okay, small the magnitude of error, higher will be the accuracy, right? We know this. If the error is small, we get more accuracy. Okay, now let me tell you one thing. Let me write it here. More the number of nodes, more will be the accuracy. Okay, okay, but more computations. What does it mean? It means, now if we have more number of nodes, okay, it means we will have more number of unknowns, right? Because we, for example, in our beam case, we calculate the displacement y at what? Y at nodes, right? So when more will be the nodes, we have to calculate the more y's, right? More will be the y's. Okay, so when the computer, the Ansys program, has to calculate more y's, okay, so of course it will take more time. Okay, and when the number of nodes will be more, okay, the accuracy will be more, because it divides the beam into even small parts. Okay, right? For example, let me tell you this, let me show it here. Now let us consider two scenarios. Let us say this is beam. Okay, now I am using the Ansys program, and I am using these nodes 1, 2 and 3. Okay, let us say this is the center. Okay, now the Ansys program told me that there is no displacement at this node. Okay, it told me, it calculated that there is no displacement here, and it told me that there is some displacement here. Let us say this. Okay, now what? Let us draw the deformed shape. You see, we have just only 3 points. Okay, and also the Ansys told me there is no displacement here. Okay, so I don't know, maybe I will draw it here like this and like this. Okay, now let us consider another scenario. Here we have less nodes. Okay, now let's consider another scenario. We have more number of nodes now. See, let us say this is the center. Now the we have here what? More nodes. Okay, now because we have more nodes, the Ansys will calculate the deflection of each and every node, right? So the Ansys told me there is, for example, no deflection here. The Ansys told me there is some deflection here, and then told me a little deflection here, then told me a little deflection here, then a little deflection here, then a little deflection here. Similarly, I got these deflections, okay, and there is no deflection, okay. Now when I draw it, okay, now tell me which is, now this is our deflected shape, okay. Now which, tell me which is more accurate. Is this deflected shape more accurate, or is this deflected shape more accurate? You will say yes, of course, this deflected shape is more accurate, okay. Now we got more, more density of these nodes, okay. We got more points with, okay, the displacements, so we will get accuracy. Since we have less nodes, we will get less accuracy, okay. So this is fast, okay. Why it's fast? Because it have only 3 nodes to calculate. Now it have multiple nodes, so it will take more time to calculate the deflection at each, right? Because they are more, so here it is slower, right? But more accurate. Here it is less accurate, okay. So anyways, so I have told you, let us summarize here. I have told you in the analytic method what we do. We have a differential equation, right? Differential equation, okay. Now this is not just the summary of what I said, I will add more points here, okay. We solve it, okay, and we get our unknown, okay. For example, y in case of beam, okay, displacement in case of a beam, okay. It can be the stress at the points of beam, it can be the shear force at different points, it can be the bending moment at different points, okay. So but in Ansys program, it uses finite element, okay, analysis, okay. Okay, what it does, it divides the body into what, into finite elements, okay, finite elements, and calculates, for example, y in our case, displacement at each node, right, each node from the equations, which simultaneous equations, okay, set of equations, okay. Now we in Ansys we represent simultaneous equations in the matrix form, okay. And as I have told you before, we will not go into that, okay. That is not, I think, important. We just need to understand how the Ansys work, okay. So okay, now if our, you know problem is simple, okay. For example, problem is simple. For example, simple shape, simple shape, okay. For example, our engineering product, okay, it is like a rectangle. For example, it is simple, okay, it has a simple shape, okay. Now we will use analytic method in that, okay, because it is a simple shape, okay, it is a simple engineering product. The differential equation is also going to be simple, okay, and it will be easy, okay, easy to solve, so we will get our y. Now what happens in case we have a complex problem, okay. Now let's say the problem is complex, okay. For example, complex shape, because the engineering products in real life are not simple, okay. They are not the basic shapes or anything. For example, let me tell you, a bridge. We know a bridge For example, a truss bridge, for example, let me consider this truss bridge. Excuse my handwriting, just try to understand. Let's say this is a truss bridge. Okay, now you can see here we connect these 2 points, for example, connect these 2 points, then we connect these 2 points. Now here you can see this is a bridge, right? Now what is this? Is it simple? Is it a simple shape like a simple square or a triangle? It is not, right? It is complex shape. Okay, so in this case, even if we decide, okay, we will not use the Ansys program, we will use the analytic method, okay, then this differential equation is not going to be simple. Okay, it is going to be what? It is going to be complex differential equation. Okay, since we have a complex differential equation, it will not be easy to solve by hand. Okay, not easy, it will be complex, or let me write as hard. It will be very hard to solve for y. Okay, we will, because we will have a complex differential equation. As I have told you, for example, in Macaulay's method we use m is equal to ei d square y by dx square. Okay, this is a differential equation, right? But here this is very easy. Okay, we will solve it, we will put the end conditions into it, and it will be easy. But when we have complex structure, okay, then this equation will not be like this. Okay, very easy, it will be, okay, it will be perhaps, the third power of differential. Okay, then there would be multiple terms. Okay, and all of that, it is going to be very complex. Okay, a complex differential equation. Okay, then because it's a very complex differential equation, what's going to happen? It will be very hard to solve for y, right? Then if we try this, it will take us a lot of time to solve it, and even after that we will not be able to do it perfectly. Okay, even we get this, accurate y, right? I have told you in analytic method we get accurate y, right? But when we try to do this complex, this will be wrong. Okay, we will do mistake somewhere. Okay, so to handle this, what we will do, here in this complex shape we will use Ansys. Okay, because it uses finite element analysis. Okay, it will convert every part of this, every component of this truss, for example truss bridge, into what? Into finite elements. Okay, for example this, it will place nodes, and then it will calculate all the required results, for example whatever we need. Okay, so that is the main difference. Okay, so we will use Ansys because in real life we don't have simple things. We will use Ansys program or another programs. Okay, because we are talking about Ansys, so we'll focus on Ansys. Okay, so this way we will use Ansys. Okay, we will not prefer analytic method. Okay, so now let me tell you more about this. Okay, what does Ansys do? Ansys do, let me tell you, let me add more points here. It divides the body of into finite elements, right? So for example, let us say this is our, for example this is our beam. Okay, I am showing it in 2D plane. Okay, this is our frame. What it will do, it will what? It will convert it into, let me show it here. What it will do, I will show it here. It will, you know it will what? Divide it, right? Divide it into finite elements. Okay, let me draw these. I will show you what these finite what is this. Okay, now you can see this is, we call this as meshing. Okay, let me write here, it is called as meshing, or I think discretization. Okay, discretization. Okay, simple word, you can call it as meshing. Okay, meshing means divide the body into, now this is one finite element, right? This is a finite element, and it is a plain finite element right here. Okay, this is another finite element. Okay, and these are the nodes, right? These are the nodes, right? All of these are nodes. Okay, okay. Now for example, if we want to see the deflection in the center, for example this this is the center line, and we want to see the deflection when we apply a load on it, and we will tell the Ansys to tell us the deflection in the center. Okay, so we have these nodes here, the Ansys will calculate the deflection at these nodes. Okay, because this is the center line and it will give us the deflected shape. Okay, like this, right? Similarly, we can uh, tell the Ansys program to calculate the deflection of the whole shape. Okay, then it will consider all these nodes. Okay, see the deflection of each node. Okay, then it will see the deflection of each node. Okay, like this, then it will, if we connect it, okay, here it is our deflection of the whole beam. Okay, so we call this as meshing technique. Okay, now the good news is what? The good news is the meshing, you know, this meshing, it is automatic. Okay, mostly in Ansys. Okay, so it is, you don't have to worry much about this meshing. Okay, because it will do the meshing automatically. Okay, mostly, and in some cases we have to modify the meshing. Okay, we might will increase the density of these nodes. Okay, if we want the more accuracy. Okay, or sometimes we will choose the shape. Okay, right now if you see what is the shape of these elements, it is what? Quadrilateral, right? Then in some cases the shape can be triangular. Okay, triangular. Okay, then if we need more accuracy, the Ansys will put more nodes. Okay, now this is called as uh, first order. Now this is not important. Okay, first order. Okay, tri element. Okay, plane element, we call this as plane finite element. Okay, then if we want to increase the accuracy, then what we do, besides on the edge, it will increase, it will put more nodes. Okay, then we call it as second order. Okay, second order, again I'm telling you it's not important. Okay, now if we have this line element, now this is what? Line element, then this is known as, because we have only two, this is called as first first order. Okay, now if we want to increase the accuracy, we will put more nodes here. Okay, then it will be second order. Okay, same is in the 3D. Okay, in the 3D views like this. Okay, these shapes, anyways it is automatic in the Ansys. Okay, and we will talk more about these finite elements as we move on. Okay, so I think that's it for today's class. Did I miss anything? Please comment if you didn't understand anything, and if you need any help in Ansys project, you can contact me if you need any help, and I will definitely help you. Okay, so I think, let me see if we cover everything. Okay, so I think that's it for today. and see you in the another class. Thank you.